Hey, let's look at problems number 3 and 4 right now. These are really an extension of 1 and 2, just couched in some word problems. So here we go. So we've got the angles of elevation are 42 and 36 from level ground to the top of a tower on opposite points. So what we have is some tower in here. And the angle of elevation on one of them is 42, and the angle of elevation on the other one is 36. Now, there is sort of an implication there that since this angle is a little steeper, that means this side is a little closer to the tower than that side, although we don't know by how much. And it says the two observers are separated by a distance of 94 feet. Well, what I know then is that we actually are given an ASA triangle, which means we actually have the ability to use a little bit of law of sine. So I'm going to start with my 180 degrees that I always have in triangles. Let's take away 42 and 36, and I just found that 180 minus 42 and minus 36 gave me a central angle of 102 degrees, okay? Now, that means I could utilize that information to solve for a missing side. So what I'm going to choose is I'm going to say then that the sine of 102 over the opposite side, 94, is equal to the sine of 36 over maybe x. And you could name it something else if you wanted to, but that's just kind of how I picked. So that means that 94 times the sine of 36, you'll notice I'm cross multiplying, divided by the sine of 102, that is going to be x. Again, I just took x times the sine of 102 is equal to 94 sines of 36. Again, I did this divided by the sine of 102, and I just found out that this x right here is 56.486. Now, that sounds like we did a good job, but we're not quite there because it didn't ask for all that. It said, can we find the height of the tower right here? Well, what works pretty nice then is that I know that this is a right triangle, because assuming that the tower is at a right angle, then I could just say regular old sine, the sine of 42 is opposite, which would be the height of the tower, divided by hypotenuse, which is 56. And I have that information right there. So if I just took the sine of 42 right here and multiplied it by this 56 that I already had on my screen, then the height of the tower is 37.796 meters. And we're done. Now, number 4 is a problem that's historically really baffled a lot of people, and it kind of surprised me how hard it is. But we're talking about a little baseball game. And I don't know why they call it a pitching, like a baseball diamond when it's not really a diamond. You know, it's just a square. I was looking for a nice square that I could draw over here. But we've got this little thing right here. Here's my baseball diamond. We've got home plate right here. We've got first right here. We've got second right here. We got third right there. And it says that in Little League, by the way, this is true, that the sides are 60 on a side, okay? So every time you run 60. And it said that the pitcher's mound is on this line, but a distance of 46 feet away. So I'm just going to put 46 right here as being this distance right here. Now, I think what most people believe is that that pitching thing is right in the middle of first and third. It doesn't say that. It doesn't say in the middle. It just says 46 feet down. Put that a little bit higher. Well, but because of how this works, this is a 45-degree angle between these two things. So you'll notice the side angle side. So I want to know how far is it from the pitching rubber right here to first base. Well, you'll notice the side angle side. So what I'm going to do is I'm just going to use the law of cosines. And a squared plus b squared minus 2ab cosine c. There we go. Now, just like that previous video, I can just multiply this all out like crazy. 60 squared, 46 squared, minus 2 times 60 times 46 times the cosine of 45. I got this big number, but that's x squared, so I'm going to take a square root, and I have found that the distance is 42.6. 42.5, actually let's go 8 feet right here. Now, how far is it from the pitching rubber to second base? Well, that's actually an easier problem because I should know that this is half of a square. So the distance all the way from home to second should be 60 square roots of 2. I also know that from home to the pitcher was 46 feet. So all I really need to do is take the entire distance away, 60 root 2 minus 46. And so we find out that that's 38 feet. So from the pitching rubber to second base would actually be 38.85 feet, which means that tells me that the pitcher is actually a little closer to second base, and they do that to protect the little person that's pitching. Because if somebody hits a hard ball and it's a young child, they may not get their hands up in time to protect themselves. So sometimes you'll see a pitcher get hit by a line drive pretty bad. Now the last question, again, let me go ahead and redraw that a little bit tighter. We all of a sudden know that this is 46, this is 42, and this is 60. The question is, if the pitcher is looking this way, how far do they have to turn to throw that ball to that person? And again, we know this is 45. So looks to me like I've got a lot of information, so I should be able to use the law of sines. The sine of 45 over 42 is equal to the sine of the angle that we're interested in divided by 60. And this is okay because I know that it's further back, so it won't be obtuse. And we did talk about that in class. So 60 sines of 45 divided by 42.58. You'll notice, oops, I made a mistake there. 60 sines of 45 divided by 42.58. I got a number very, very, very close to 1, which is kind of interesting. But if I take the inverse sine, I got 85 degrees. So theta is 85.13 degrees. Now, if the pitcher had been right in the middle, it would have been a 90-degree turn. But since they pulled back a little bit, they had a little bit under that 90-degree turn. And that finishes page number 2. All right, I'll see you soon.